David, you ready to start?
Yeah, absolutely.
All right. Hello, everyone. Thanks for making it here on a nice, crisp Berkeley morning. It's my pleasure to introduce David Gamarnik, who until very recently was my only office mate, and now I have an empty office with just me. And he's going to tell us about a curious case of a symmetric binary perceptron. So take it away, David.
Thank you, Ashwin. And yeah, good to see everybody. Well, good to sort of see you. I missed already great interactions at Simons. I had to be back for teaching, and I only wish I could spend the whole semester there, as many of you do. So enjoy it while you can. It's a pleasure to share with you some recent work. It's actually work in progress, and I'll explain what part of it is still in progress as we progress. No pun intended. And it's called the Curious Case of the Symmetric Binary Perceptron Model. I will explain what's curious about that. This is a joint work with Aaron Kizeldak, my student at MIT. He should be somewhere in the audience. So, okay, good. Right. So, Aaron, okay. So if there's any questions from the audience, Aaron will be happy to answer them. It's also with Changji Xu, who is a postdoc at Harvard, and Will Perkins from the University of Illinois in Chicago. Most of you probably know Will very well. Okay, my battery is almost dead, so just a second. Okay, just like yesterday's Lenka talk, I want to start by acknowledging Giorgio Parisi receiving a Nobel Prize. That's an incredible news for us. As needless to say, Giorgio is an incredible contributor to the field, to our field. So it's not just physics, but his name has been mentioned many times in this and previous workshops because of his fantastic contribution to the structural and algorithmic ideas in the random structures and optimization. And this work is actually not an exception for that. And so I thought, as my own tribute to Giorgio, I'll do my own rendition of his picture. So I have to say that my handwriting skills is not that good. But my drawing skills are even worse. So you please. Maybe I'll give him a little bow tie. I think it's appropriate. So, all right. So, Giorgio, great news. Okay, now slightly on more serious note. There's a word perceptron in the title. Just a brief history of that. Arguably, perceptron marks the birth of the machine learning field. It was introduced by Frank Rosenblatt from the University of Cornell in 1958, and it was implemented on this little machine in IBM, a little machine. You can imagine it's several rooms large. And it was supposed to do the recognition, face recognition, or I think maybe some kind of an image recognition, I don't remember. And it was arguably that marked the birth of the machine learning field. This was so amazing that back then the New York Times wrote an article about that, and I quote here. The New York Times reported that the perceptron will be the embryo of an electronic computer that the Navy, of all things, expects to be able to walk, talk, see, write, reproduce itself, and conscious of its existence. And this is 1958. So as you can see, the doomsday scenarios of machines overtaking humans is not something new. It goes back ages. Anyways, a little bit of history on that, and back to our business. Don't worry, this is not going to be an applied talk. We're going to just talk theory. Right, just a little digression. Okay, so let me introduce the model, the binary perceptron model. So it's binary is in reference to the solution space being a binary cube. So we're going to fix a binary cube of n dimensions. Okay, then we fix a matrix which is m by n, a matrix. We also fix a subset of a set of real values R, and our goal is to find sigma in the binary cube such that so when we hit this matrix with the vector sigma, it lies in the set C to the power n. So in other words, for every row, when you hit it with the vector sigma, it belongs to the set C. And the two common examples that have been considered in the literature, and the ones we will consider today, are the following special cases. This case one, and this is going to be the main focus of today, is when C is just a symmetric interval around 0. And we will refer to it as a symmetric binary perceptron model. But I will also mention another case, case two, when C is just a set of non-negative reals, which is referred to as symmetric binary perceptron model. Okay, so in this case, you need to find the vector sigma such that A of sigma in L infinity norm is in the interval from kappa minus kappa to kappa. And I will also use a normalization, square root n normalization, in anticipation of the scaling that we will be interested in. And that's a natural scaling to do. We will see why. All right, so just algorithmically, you have a matrix, you have a set, you want to find a binary vector such that when you hit the matrix with this vector, it lies in some subspace of Euclidean space. And that's the problem. Now, naturally, we will focus on the case of the random instances, and in the random instances, we are interested in the cases where entries of the matrix are either normal, standard normal, or they are Rademacher. Plus minus 1 with probability 1/2. So Rademacher. And then the variables, I will freely go between the two cases because for most of the part it wouldn't matter. The details of the distribution for many of the things I'm about to say don't matter. In some cases, they do. It's not surprising that many of the things are exhibit universality property, where the details of the distributions are irrelevant as long as the first two moments match. The first moment here being 0, of course. So if you have this model in mind, then the kappa being constant makes sense, because if you take matrix A 1 over square root n times sigma, then each row, and you get a vector, each entry of this vector is going to be standard normal if Aij is standard normal. So you want to make sure that all of such standard normals are in the interval between minus kappa and kappa. And of course, that's automatically wouldn't be the case, because the extreme of the Gaussian is like square root log n. So it's not by no means obvious that such a thing is possible. Okay, so that's this is the model, and the questions we want to ask are fairly standard questions that we ask in this conference. So the first question is of existence. And let me introduce the notation. Let sigma of A the underlying set where we want the vector to be is, I'm not gonna make it part of notation. This is all sigma in the binary cube, such that a sigma is normalized by square root n is in the set whatever set we care about. Okay, so it's a set of satisfying vectors, satisfying solutions, satisfying solutions. All right. So the questions of existence is that is A empty or not? And that's the first question. And the second question is algorithms. If we somehow know that such a set is non-empty, can we actually find such a vector? Okay, and because this solution space is here is binary, it's not obvious a priori that such a thing can be done, as opposed to the classical Rosenblatt's case, where if there's a linear separator, you can actually find it by many ways. All right, so this is the model. It obviously goes without saying. If you have any questions about the model, go ahead. I hope the model is clear. But any questions on the model before I turn over and share with you what we know about this model? Mostly, I will talk about the symmetric case. So let me actually start now with the give you some background. And for the symmetric case. So in this, this means that we want to all entries of the vector to be in the interval minus kappa to kappa. So first, so we're going to consider, for both symmetric and asymmetric case, we're going to consider the proportional regime. And that means that M, the number of rows, is going to be some alpha times n, which is the number of columns, and alpha is going to be fixed. And so what do we know about that? The fairly straightforward argument shows that the solution is empty with high probability if alpha is bigger than alpha critical, and alpha critical is actually log 2 divided by absolute value of log kappa. Okay, in particular, it scales like order 1 over log kappa. So where is this coming from? It comes from a very straightforward analysis. You altogether you have 2 to the n solutions in the binary space, and you look at the sorry, I made a mistake here. It's a bit premature. The denominator here is the probability that absolute value of the Gaussian is at most kappa. Okay, so I jumped too fast. So,
David, we need an extra log, I guess, in the denominator.
I'm sorry?
We need an extra log in the denominator.
Thank you.
Yeah, with absolute.
Thank you. Yes. So this comes from, absolutely. So this comes from the fact that, okay, each row upon hitting with the binary vector becomes a Gaussian. This Gaussian needs to be in the interval. So you have this condition, and all of this needs to happen for the alpha times n different rows. On the other hand, you have 2 to the n different solutions. So you want to, at the very least, make sure that this goes to infinity, as n goes to infinity. And if alpha critical is reversed engineered from that. So if alpha is bigger than 1, the expected number of solutions goes to 0. So that's kind of obvious. But what is not obvious is actually this alpha critical is tight. And this is a fairly recent result by Xu, Changji Xu and Perkins, or Perkins and Xu. I'm sorry if I changed the order inadvertently. So, and simultaneously, Abe, Li, and Sly, also in about the same year, they have shown that in fact, alpha critical is tight. And what it means is that the probability that the solution space is non-empty actually goes to 1 and then goes to infinity when alpha is less than alpha critical. Now, that sort of comes from the second moment analysis, but not quite. The second moment analysis gives you that this probability is bounded away from 0. But if you actually want to argue the tightness of that, you have to do more work, and this is what has been done. But something else really interesting, I think, emerged in these two pieces of work, and that has to do with the clustering picture. The familiar clustering picture that we keep discussing in the context of various constraint satisfaction problems. And we can think of this also maybe as a constraint satisfaction problem. So what they have discovered is the following. So horizontal line will correspond to alpha. You have alpha critical here. Actually, let me move it a little further. Okay. So you have alpha critical here. And here that corresponds to the unset regime. What they have discovered, perhaps not surprisingly, that before the alpha critical, there is if the solution space is split into clusters. Not the entire solution space, most of the solution space, and I will explain. I'll explain. Okay. So what they have discovered is that somewhat more formally, you can find a subset sigma hat over sigma, which is almost the entire space. So the ratio of sigma hat over sigma is at least 1 minus exponentially small in the number of columns, such that in this subset, all solutions are in fact singletons. So that's why I draw them as little dots as opposed to circles, singletons separated by extensive differences of order n. Okay. Now that is in reference to this big subset of the solution space. Admittedly almost the entire solution space, but not everything, which means that potentially if you include everything else that has been omitted in the solution space, then this is no longer true, and you can have some little like tunnels here connecting various singletons. But modular this exception, this model exhibits an extreme form of clustering, where each cluster actually consists of a single dot. Alternatively, you can say that the number of rows, the percentage of rows and variables is 100. This is in references of so-called frozen variables in clusters. Maybe not something familiar to all of you, but if you've seen this stuff before, you know what I mean. Now, here's this is perhaps not surprising. The most surprising thing about this is that actually happens above 0. So this picture I've described holds for, this picture I have described holds for every positive alpha. And you can contrast it with the picture that you see in the random k-set model. And I want to do this comparison, and I will explain why I think it's an interesting comparison. Okay, but before I do that, you might ask, and we'll come back to that, whether there exists a different phase where this clustering does occur, that should be at a higher threshold value, where this clustering occurs and without exception. Is that the case or not? I'm asking that because that is the case for the random k-set model. So first, any questions about what I drew here? So this picture is an implication of these two pieces of work by Perkins and Xu, Abeli, and Sly. Okay, now let me remind you what we know for a related similar problem of the random k-set. Random k-set problem. Okay, so again, we have a critical alpha. I'm not going to define what random K-set is, so I'm kind of hoping that many of you have seen this this before. Again, there is a phase which is unset. And there is, but now the onset of clustering, so call it cluster, unlike in the perceptron model, happens at a positive density. So you have, which means that below that, the solution space is mostly connected. Maybe there's some exceptions here and there, but it's mostly connected. Whereas here, the solution space is most of it disconnected by order and distances. So you have clusters. The clusters are no longer singleton, so it's not 100% of variables are frozen. Most of them are frozen. And that again applies to the majority of variables and majority of solution space, which means that some tunnels between the clusters might occur. But in fact, provably, there is another phase here. Another phase. And actually, let me call this type of phase as a weak clustering. And let me call this strong clustering. So strong is in reference to no exceptions. So in this phase, what do we have? In this case, we have these clusters of solutions, but there's no tunnels between them probably. All 100% of the solution space is clustered. What's the relevance of this and why am I spending so much time on that? The relevance of this is the potential algorithmic implication of all of this. For the case of the random K-set model, there is a fairly strong evidence then that the algorithmic hardness occurs actually here at the onset of the weak clustering. The most recent confirmation of that is in the work of Guy Bressler and Bryce Kwong of this year, who showed that pretty tightly at this threshold, many of the algorithms that we know, like low degree polynomials type algorithms, fail. Okay. And that's not very surprising. This line has been conjectured to be the onset of the algorithmic hardness a while ago already. So that's not a surprise. Okay, so it presumably weak clustering property is the onset of hardness. If that's the case, if we go back to the perceptron model, maybe the problem is hard for every positive density alpha. And that's the curious part of this talk. The answer is no. There exists positive alpha for which the problem is solvable. So let me share with you what we know about it. Okay, so the answer is no. How do we know that? First, a while ago, in the heuristic study, the empirical study by Braunstein and Zekina, and this is 06, they did experiments, and these experiments revealed that it seems, at least experimentally, that the perceptron model is solvable at some small but positive density, even though we know now that it exhibits a clustering. Okay, but then later this was confirmed, and the paper that the most relevant for us today, that I will spend more time on, is by Bansal and Spencer. Bansal and Spencer appeared in 20, posted a little earlier, and the Bansal and Spencer work shows that indeed there exists a positive alpha for which the symmetric, so this is in reference to the symmetric model. So we have kappa here, that for each the critical kappa has to be at least as large as something, and you can show that this something as in size of the interval goes to 0 is actually quadratic in kappa squared, quadratic in kappa. Okay, so it's a positive result. They construct an algorithm, very clever one, that shows that indeed symmetric perceptron model is solvable at some positive density. The critical value here, therefore, for the symmetric perceptron model is at least order kappa squared. So that at the very least, I guess, suggests that showing this picture that we have here as an evidence of the algorithmic hardness, in other words, the onset of weak clustering as evidence of algorithmic hardness, that flies in the face of this picture, where we have the weak clustering occurring in at every positive density. Yet there are algorithms to solve this. So let me pause here before I sort of recollect my thought. Let me pause here and ask if you have any questions. Okay. So, all right. This is not an exhaustive list of the positive results on the symmetric perceptron model. In fact, there is an earlier work by Lovett and Mecca from 15. They also construct an algorithm that solves the symmetric binary perceptron model, but their analysis seems to be applying only in the case where the number of rows is bigger than number of columns, and that cannot, therefore, from that it's hard to figure out what's the implication when kappa goes to 0, because if kappa goes to 0, that the critical alpha goes to 0 as well. That means that you have to work with way fewer rows than columns, and that kind of makes sense. If you want all your answers to be in tiny little intervals, you cannot afford to have too many rows in your matrix. So let's summarize. So what do we have? First, we have a critical alpha. So this is again in symmetric binary perceptron model. We have a critical alpha C, which looks like this. It's log 2 divided by the log of the probability that standard Gaussian is at most kappa. So we're going to call it alpha C of kappa. As kappa goes to 0, this becomes approximately log 2 divided by the log kappa absolute value. So let's keep the scaling in place. Okay. So this is as far as the existential result is concerned. On the other hand, as I said by Bansal and Spencer, the implication is that as long as alpha is less than or equal to something of order kappa squared, the solution is non-empty with high probability. So there is still a big gap between kappa squared and log 2 and something which is here, which is order 1 over log kappa, absolute value. So the positive results exist up to here. Existentially, we have it up to here. So we have a gap, right? So clustering aside, we have a gap. And can we explain this gap? some way, and that's what I want to report. We're going to take, surprise, surprise, we're going to take the approach of the overlap gap property, which I will explain shortly. As a side remark, there is a reading group now ongoing at Simons by Bryce and Aaron on this. So if you wanted to know more about this, I would refer you to this reading group. So we want to take the overlap gap property, or put it more generally, a different landscape approach to try to understand the true algorithmic hardness of this problem. Okay, right. So here's what we know. Let me state it in a theorem. This is going to be likely the only theorem that I'm going to formally state. It's going to be long. Bear with me, please. But then I'll state the theorem formally. I hope it's it's correctly stated. Aaron will correct me if something is not accurate, and then I'll give the intuition. So here we take the kind of full sort of power of the OGP approach. The theorem is stating that a model exhibits the so-called symmetric ensemble multi OGP. Probably very little of this makes sense at this stage, but I'll explain. Okay, so recall we're dealing with a symmetric model, so we have parameter kappa. So the claim is that for every small enough kappa, there exists a critical number, let me call it non-creatively as alpha OGP of kappa. It's going to be certainly less than critical value for the existence of the solution. I'll say much more about that, how much below it is, such that the following is true. However, if it takes alpha slightly larger than the critical value, I apologize. I have to do the digression into okay. Sorry. I have to first introduce an ensembler version of the model. So I guess I'll come back to the theorem and introduce the ensembler model. I will do it only for the case of the standard normals. So every entry of the matrix is standard normal. So here's what we're gonna do. Let's create another matrix, A hat, which is independent from the original matrix A. And let's create an interpolated family of models, A of t, which is defined as follows. It's a cosine of t times A plus sine of t times A hat. Okay. So in other words, we have one matrix, we have another matrix. This is A, this is A hat. And now we create this whole family of matrices, A of t, in between. And one thing to observe is that the entries of each of such matrices are against standard normal, because the variances match. Okay, so that's what we have. So we have this interpolated family of models. And the theorem is in reference to this interpolated family. what's the significance and so on, that's to be discussed. But let me now state the theorem. So for every alpha larger than this claimed value, there exists a large enough constant, integer constant m, such that I'm reaching the limit of the number of quantifiers that I've ever had to use before, and more quantifiers are coming. There exists a number m such that for every sequence of numbers starting from 0 up to pi over 2, why pi over 2? Because as t is equal to 0 in this interpolated family, we have the first matrix, and when t is equal to pi over 2, we have the new freshly independent matrix. So this interval goes as t spans from 0 to pi over 2. Okay. All right. So if you fix any time instances in this interval, so there exists an m such that I made a mistake for every sequence of such numbers, and for every sequence of solutions, sigma 1 in instance associated with time 1, sigma 2 in instance satisfying assignment with respect to the instance at time 2, and so on, sigma m associated with the satisfying assignment at time tm. There exists an m, okay, and all right, something else is missing here. There exists m and two numbers mu1, mu2 less than 1, such that anytime you have this, it is also the case that there exists two numbers k and l between 1 and m, such that the inner product of sigma k and sigma l normalized by n belongs to either the interval from 0 to nu1 or interval from nu2, let me write it cleanly, nu2 to 1. Okay, now if you were able to parse what I have here upon seeing something like this for the first time, I would be hugely impressed, because this is probably nearly impossible to say what this even says, let alone understand its significance or implication. So now let me try to, yes.
Where's the probabilistic quantifier? I mean, where do I?
Good. I missed that. There exists. So that existence is with high probability.
But do I pick the is before picking the endpoints or after, or? I think the high probability
is with respect to the randomness of the A and independent copy of A. Once you fix A and fix a copy of A, the interpolated family is deterministic, is conditionally deterministic, and that's in reference to this random. That's the only randomness.
But they happen at the end. So this prohibited interval V1, V2 is chosen before choosing picking A and A.
Okay, good. Thanks for asking. I think it's Nazi, right? If I'm here. Yes. Okay. So all of these parameters are deterministic. Nu1 is this. All of these parameters, alpha OGP, nu1 and nu2 and m. These are all m, nu1, nu2 are all deterministic. They're fixed up before. Deterministic meaning only kappa dependent, but nothing else dependent.
K and L, are they also deterministic, or K and L dependent?
No, no, they're not. They're not. KNL. No, they might depend on how you actually have drawn such solutions sigma. So you fix any collection of times. Let me come back to that maybe when I try to give some intuition, if that's okay, and maybe that will clarify also what is random and non-random here. Okay, so what is happening here? First, as a warm-up, let's consider the case where m is equal to 2, and we just pick two identical times. T0 is equal to T1. Did I start with T0 or T1? Doesn't probably matter. T1. Okay. So let's suppose we just look at the special case when 2 times are equal to 0. In other words, we're just dealing with a single instance case. So the implication of that that is very simple. As long as you take 2 satisfying solutions in the symmetric perceptron model, it should be the case that they're in a product normalized by n is either in 0 from nu1 or nu2 to 1. In other words, exhibits a gap. And geometrically, that's very simple. That basically says that okay, so pairwise distances for every 2 solutions, pairwise distances have to be either small or large. So pairwise distances, small, quote unquote, or large, quote unquote. Okay, so that was easier, but I realize it doesn't quite answer the question that Neti has raised. So let me now come back to the theorem, and now in a pictorial way. So here's what we do. Here's the dynamically what happens. We draw a copy of A. That's a random copy. We draw another copy of the same randomness A hat, which is independent. We construct a sequence, continuous sequence of models. So in parameterized by time, continuous time, going from 0 to pi over 2. So each of these corresponds to A of t. Fine. Okay. Now, right. So then we fix any numbers, T1 and so on, Tm. So in other words, we fix collection of instances here. Maybe this one, and this one. Any m instances in this continuous family. We pick for each instance, we pick any solution. So sigma 1 is in here, and so on. Sigma m is in satisfying solution with respect to the mth instance. Those could be picked arbitrarily as long as they are in a satisfying set. So those are picked. So we pick the vector here. We associate with this instance, the vector associated with this instance, the vector associated with the instance. So we have the whole bunch of vectors in the binary cube. One vector, sigma 1, sigma 2, sigma 3, and so on, sigma m. We look at the pairwise distances. All m choose 2 of them. And all we're saying is that there should be 2 instances, just 2 of them, for which the distance or the overlap is not in the intermediate interval from nu1 and nu2. Nati, is this good enough?
Yeah, no, I think it was clear. Can you remind us? So at least me, is mu1 and mu2 the period interval does it depend on m, or is it? Can you show the theorem again, please? Just to all the quantifiers. Can you scroll back to all the quantifiers?
Yes. Right. There exists m and nu1 and nu2. So both m and nu1 and nu2 depend on kappa.
Okay.
Okay. All right. So I know I'm running out of time, but let me tell you the punchline of all of this. Well, there's actually two punchlines. One is not very surprising to many people in the audience. One is perhaps surprising. So first is that why would we care about structure like that? Because using the structure, we can rule out classes of algorithms, and that holds here as well. So the presence of this multi-symmetric, multi-ensemble OGP rules out stable algorithms. Now, there's one algorithm I didn't mention earlier it's for the admittedly for the asymmetric model Kim and Rouge. We can prove that this algorithm is stable, although it applies to asymmetric model, not symmetric model, so its implication is not entirely clear. Bansal and Spencer algorithm appears to be symmetric. This is the work in progress, but we believe we have an idea to show that in fact it's symmetric. But the implication is there. So once the multi-presence of the structure can be used to rule out algorithms. This is not very surprising. Perhaps the novel part and interesting part is that if you work out the critical kappa, so here we have critical, if you work out for which kappa, for each kappa, for small enough kappa, where is the onset of the overlap gap property, that turns out to be kappa 2 minus little o 1. And if you contrast it with this Bansal and Spencer algorithm, that works up to kappa squared. So in this landscape, in this one-dimensional parameter, remember the critical is something of the order 1 of the log kappa. The algorithm exists, so the algorithm exists by Bansal and Spencer when alpha is of the order kappa squared, but pretty much immediately after that, we have the OGP regime indicating that likely the problem is hard. So the OGP picture here provides a fairly tight characterization tied with respect to the known algorithmic threshold. Okay, I think I'm over my time, so perhaps I should stop here and take questions.
So this symmetric multi-ensemble OGP. So this characterizes the difference between the weak clustering and the strong clustering.
Good. So no, neither. So let me actually thank you. I think it was Miklos. Thank you for reminding me of that. So the multi-OGP picture by itself is not. I don't know how to describe it in terms of the clustering property of a kind. However, if you look at the 2-OGP, so in the case where at least two pairwise solutions are in a product is disconnected, the onset of the 2-OGP implies strong clustering. So what it means is that in this context, remember I posed this as a question mark. There is no question mark. So we know there exists a strong clustering property for the symmetric binary perceptron model. It does happen, but it happens not at the algorithmic threshold. It happens much at a larger value, at least for computation, at the values larger than kappa squared. We don't know exactly how it scales with kappa, but it doesn't get all the way to the algorithmic threshold. And the algorithmic threshold is somewhere here, which is, again, it's hard to connect it with the clustering picture per se.
Thanks. Thanks. So the 2OGP and this MOGP would be different thresholds?
Oh, yes. Yeah, that's right. Sorry for not clarifying that. The reason we needed it to go, and this is historically, let me actually mention several pieces of work I meant to mention in reference to the multi-OGP picture. One is by Alex Wine in the context of independent set. I mentioned already Bressler and Huang in context of the K-set. And there is a more recent work, which I guess will be posted soon by Bryce and Mark Selk in the context of P-spin. In all of these papers, the multi-OGP structure is introduced and proven in order to match the algorithmic threshold, and multi-OGP does occur at the threshold lower than the 2OGP.
Great, thank you.
Hey, David, great talk. Can you give some intuition for what Bonsall-Spencer is doing and like maybe how it's navigating the
Good.
clustering regime?
Good. So, right. So not gonna have time to go into details of the algorithm, but let me describe it in high-level terms. But you also remind me something else I wanted to mention. It is noteworthy that both Kim and Roche algorithm that I barely mentioned here, but also Bonsall and Spencer algorithms, they are not instantiations of the low degree polynomials. Otherwise, our work will be easier because we already know how to rule out low degree polynomials. They are not. So we have to conduct an independent stability analysis of that. So Bonsall and Spencer algorithm works like this. So you have a matrix. This is matrix A. So you have columns. You essentially set up values. So for each associated with each column, you need to set up the value of the sigma, which should be plus minus 1. Essentially, you do it in a dynamic way from the left to the right, where you sequentially set each of the values of the sigma based on the values of what you've seen up to that point. So it's online, effectively one sweep online algorithm. And this value sigma is obtained, well, there's some potential function analysis, but basically what you do is that you look at the values corresponding to the sums across previous t-1 columns, and then you set your value plus minus 1 depending based on this sign of the sum of those values. It's not a very crisp description of the algorithm, I realize, but this is basically what's going on. It's a one sweep algorithm setting the values of sigma one by one, depending on what you've seen before.
Thanks.
All right. So for further questions, you can get in touch with David later on. But let's thank him again.
Thank you.
We'll be back at 10:15. 20 minutes.